Great. And here comes Carter and Justin.
Good. Mark's also from our team, and
Great.
you haven't met him yet, but he's going to be helping with some stuff moving forward.
Okay. Hi, Mark. Great.
Hi, good evening to you.
Give it a few more minutes, only 7:01. Oh, all right. Welcome, everybody, to this meeting with Egg Geothermal to give us an update on the Speedsville Thermal Network or Community Geothermal Project. And welcome to the Egg team, and great to see you, Jay. I guess I'll let you take it away. And actually, you probably I'll give you co-host privileges so you can share your screen if you want.
You bet. Give that to Carter because he's going to be
Okay.
sharing initially.
Okay.
Appreciate that. And yeah, quick introductions. Is Pat there today? Pat Jordan?
Pat's not here today. Aaron DeBolt is here, and
Okay.
Lori Staba's in
Lori Staba, good.
Zoom
Good.
land. And there's about 7 of us here at the Speedsville Community Center.
Okay. And do you have what's the name of the the gentleman that's a union pipe fitter. Is he there?
Oh, that's Aaron, I
Aaron?
believe.
Aaron's there?
Yeah,
Good. Hi,
Aaron.
Aaron.
How are you?
Good, good. All right. Sounds like we got a good quorum coming together. Today with us, we have Justin, our operations manager. We have Mark, he's a writer and a construction manager for the company. And he was just made aware of this project. He's working on something right now that will be helpful for this, we feel, in next steps. And of course, we have Carter, our chief scientist, and I'm Jay Egg. I'm president of Egg Geo. And I want to turn the time over to Carter to get us kicked off. Okay, Carter?
Okay, great.
Great.
I'm gonna share my screen here. Hopefully get
Okay,
a
great.
presentation pulled up. Yeah, let's see here.
There you go. It looks like it could be expanded or something. Yeah.
Yeah, are you seeing just the PowerPoint, or are you seeing the whole screen with my notes on it too?
All the screen with your notes on it. And it's actually kind of centered in a vertical way right now.
It's
So,
narrow.
yeah. There you go. Now you can go to presenter mode and it should be fine.
Okay, great.
Okay.
Give me there you go. You're good.
Okay, that's better.
Yep.
Yeah, that's better.
Okay, thank you. Apologize. We usually use Teams. It always takes us a minute to figure this out. All right. Well, just a couple of months ago, we submitted the final task for our NYSERDA study on Speedsville. So I'm going to give a brief summary. How long would you like this presentation to be? Do we have an hour for this? What were you guys
Yeah.
planning?
Yeah, we have I was thinking of an hour for the meeting, with follow-ups and everything. So
Okay,
Yeah, I
great.
would say leave time for questions.
Okay, yeah.
Yeah.
Then I'll plan on 30 to 45 minutes. We have a really summarized version of this here. And then I assume there will be lots of questions and then discussion about future studies and sort of a roadmap moving forward.
Yeah.
Great.
Leave me 5 or 10 minutes for Mark and I to talk about some grant opportunities and stuff. Okay.
Okay, I think it should be plenty of time.
Okay.
All right. So tasks 1 through 3 were sort of just a kickoff. We did a big kickoff meeting March 15th. This was back in 2023. And then there was a bit of a lull in the actual analysis. But we eventually got good documents back, lots of load information for all of the potential residential and commercial buildings within Speedsville. And then we conducted a site visit. We have a picture of Jay here in a crawl space to prove it. With all of that information, we then performed a load modeling task. This is a preliminary modeling of the space heating and domestic hot water loads for all of the town structures. We used 12-month load profiles that were developed from BEST, a tool that we use to help ensure accurate loads before we design a geothermal system around them. And we estimated fuel costs and some other metrics that we use in a life cycle analysis. I believe that's task 6. This is the site plan that we worked off of with all the residential and the commercial buildings. And this is the compiled residential space heating consumption. So there are a variety of sources here. Furnace that uses propane, furnaces that use oil, electric, and then oil boilers. And then also a small load from the commercial space heating consumption with gas and propane. You combine it together, and this was our yearly heating load that we worked with. A peak of about 1,600 MMBTUs. This is the peak load that we wanted to meet. There was also an analysis done on the cooling loads, but we generally just work off of whatever the peak is going to be, which in this case is the heating. And the cooling loads came out to about 280 tons, if I remember that correctly. Part of this analysis was also understanding how many tons of CO2 were emitted with the current system in place. And that total in the bottom right there is about 545 tons of CO2 emitted, which would be essentially totally eradicated with the installation of a geothermal system. Another piece of this was determining utility costs, which go into a life cycle analysis, the results of which I'll show in task 6. So lots of data gathering here, lots of just understanding what we have to work with and what loads we hope to meet with the system. And then sort of the meat of the study is task 5, which was our source and sink analysis. Part of this, we studied the geology, hydrology, and geography, where some of the elevations can play a role into this and how we design a system. We assessed the earth-coupled exchange potential and considered a few technologies, which I'll get into here. First, the geology. There were actually some great publicly available reports on the geology for this side of New York. We are looking at a little less than 100 feet of superficial, just unconsolidated material with a really large portion of sandstone and shell that's Devonian age, and then a couple of small other shell and limestone formations down into the Hamilton bedrock. We don't suspect drilling any deeper than 1,000 feet here. And some technologies as shallow as about 500 feet. So this is about all the geology we needed to understand, and it's pretty typical for the area. The hydrology was a little more difficult. This is a USGS published map of how much water you can yield from a well. Within, I think, 20 square miles around Speedsville, most wells produce under 50 gallons per minute, which we're looking at we were hoping to get about 200 or more. This published map, though, gives us a little more hope. Speedsville is right here in the more than 100 gallons per minute section. We've contacted local drillers, and they say that that's definitely possible. It's something that we will need to look into with a test well or something here in the near future. As far as drilling goes, we spoke with the Speedsville team and listed 5 potential drilling spaces that could be used. These were spaces that they kind of just give us an idea of what sort of space we're looking at. Obviously, the more space, the more load we can meet. And these are subject to change. This was just getting us a good idea of where to start. Now, as far as the technologies go, there are a few that we considered. Generally, we include 2 in every study we do, and that's a closed loop geothermal system, and then also an open loop. For this, we also included a submerged heat exchanger option, which is in some ways a combination of the 2 and kind of a novel technology. But first with the closed loop system, traditional closed loop is a whole encapsulated system where a working fluid is contained and circulated to harvest heat from the ground. So there's no water leaving the aquifer, there's no water going back into the aquifer. That secondary fluid goes into the ground via a U pipe, which is the most standard way to do this. There are a few other formations that we could do this in. But essentially, you're mining the stable temperature of the ground. The heat transport fluid runs through the rock and then up to the surface for heating or cooling applications. It's currently the most prevalent design for borehole heat exchangers. Our analysis on this proved that it was definitely a viable option. It's a great backup for if we decide to do an open aquifer exchange system and we end up not deciding that we can't get the water that we need. Our original analysis produced a result that said we would need 152 boreholes, assuming a depth of 500 feet, and an area of about 61,000 square feet, which gives us plenty of room with the drilling space that we were given. Just in the few months since we've turned this in, however, there's been some new sensor technologies that have come out that allows us to reliably drill a lot deeper, up to 1,000 feet, or in some places even more. That could be a really great option for this area. That would reduce us down to just over 70 boreholes, and it would only take about 30,000 square feet. So that'll be something. This technology is always changing. It's sort of up and coming. There's lots of money going towards research and development in this area. So that'll need to be probably rethought in the feasibility study and in upcoming studies for this. This is the submerged closed loop heat exchanger. This operates on the same principle as an open loop, which is you take water out of the ground and you put it back into the ground after a heat exchanger. However, your production well and your injection well, instead of being separated geographically or horizontally, they're separated vertically. And there's a heat pump that's installed between two perforated sections of the pipe. So you see here in the diagram, water can come in and out of two sections of the pipe based on the season. It takes a lot less space too, generally, than our closed loop system. It's an up and coming technology as well. All of the installations that we are familiar with, they all function great. They recommend a 50-foot separation between each of these wells, and they can produce about 100. Jay, remind me, is 150 tons of heating? I think you're muted, Jay.
Yes, and up to 300 tons of cooling, depending on now I want to just say something. I know what you were saying, but the submerged component you said accidentally is a heat pump. It's a heat exchanger, just in case anybody's listening closely. So this down here is the heat exchanger. The heat pump's still up above, and I know what Carter was trying to say. So
Thanks, Jay.
Go forward. Thanks.
So our analysis results were, if the formation is capable of producing of 200 gallons per minute, which is right where we think it should, our analysis suggests that an array of these submerged closed loop heat exchangers would require at least 8 wells in an area of about 20,000 square feet. So less wells and less square feet that we would need if we decide that this technology is the way we want to go. Now, sort of our more standard geothermal technology is an open loop geothermal well. Essentially, what we're doing here is we're producing from one or many wells, depending on the load that we're trying to meet. And then we're injecting that water back into the ground after it's been used for a heating or a cooling application. This is another technology that's going to require, we're hoping about 200 gallons per minute, if not more, to make it a viable option, to make it economic. If we get up to that 200 gallons per minute, we estimate that we will require 2 production wells and 2 injection wells. We usually separate these wells by about 1,000 feet between the production and injection, and about 200 feet between wells of the same likeness. So all these technologies have pros and cons. This one would require less wells, but much greater separation, and it requires being able to yield lots of water from the ground. The other ones, they would take more space, but but they'd be less separated between the wells. There's also maintenance to think about when we're designing these systems. These open loop systems, you need to be able to get to the wellhead, and it requires more maintenance. The 70-something wells for that closed loop system, however, require very little, if any, maintenance to the actual wells. You install them, they run to a heat exchanger room, and I believe all of the maintenance happens there. Does that sound right, Jay?
That's exactly right. You once they're closed up, you never have to get to them again. So no maintenance outside, only where the headers come together, and usually in the equipment room.
Okay. So a few things to decide from here, and these will be explored more, hopefully in future studies. And like I said, there's been some new technologies that have come out that can help us decide even better. Our task 6, which is the last actual analysis portion of this, was a district energy pre-feasibility study. And that includes a conceptual model of what this would look like, a life cycle cost analysis, additional benefits, as well as a discussion on ownership, energy services, and utilities. We will also, as part of this, talk about funding and sort of a future roadmap for what are the steps here that are going to take us from the scoping study through to construction potentially. So this is our conceptual design of what a system like this would look like. At the time that this study was turned in, our open loop technology was by far the best option. Like I said, there have been some new updates with closed loop that could make that an even better option. But for now, we'll assume that we go with the open loop option. Like I said, we'd have 2 production and 2 injection wells. This fluid is pumped out of the ground and runs through a heat exchanger to a main loop that's then siphoned off to heat and cool homes, depending on the season. This is also not exactly my specialty, the design of the conceptual systems. Do Jay or Justin, you have anything else to add to this? I know there's a lot more to it. I sort of have a really surface level understanding of these loops.
Just that loops in this type of configuration can share energy easily with one another. Whereas the first building and the loop, if it's in cooling mode and it's giving off heat, then the second building, if it's in heating mode, like shoulder seasons where they might be an imbalance, then they can share energy amongst each other where it would not need any of the geothermal to draw from, to reject heat to, or absorb heat from. So setups like this, and it reduces pumping power for a single pump or single pipe configuration. There's lots of benefits for this system type.
Thanks. Yeah, I know that I think I have notes here. Commercial buildings are usually cooling dominant and residential are usually opposite. And so the ability to share heat like this can really bring down the actual amount of BTUs that we need for a system like this. That's the main benefit of these systems. And the bigger that we can get them, the more energy there is to share. So the more homes, the more commercial buildings we can get in here, the more cost savings you're going to get. So this is where the utility costs come into play. We performed a life cycle cost analysis that gives us these cumulative costs over 25 years. And the payback starts happening at about 15 years. Let me find my notes on this here. The average, if you average them all out across 25 years, your savings per year comes out to around $240,000 per year, compared to the current utility situation, with the propane, with the gas, with the boilers. About 15 years is your turnaround here. Lots of additional benefits that are talked about in the report that didn't quite make it with a whole slide and a figure here. But I mean, a system of this type, regardless of the technology you choose, will eliminate outdoor equipment. Then that equipment has high replacement rates. It's also much more storm resilient. It takes all of your outside equipment and essentially puts it inside. Your system longevity will increase. No more combustion boilers, no cooling towers or furnaces, which has a decarbonization component to it. Like we talked about with these systems, way higher system efficiency, the ability to share energy, and then the efficiency of a hydronic system like this. And then the thermal energy network wells and piping are all permanent infrastructure. This isn't something you're replacing every 10 years. It's all in the ground, it's all permanent. And most of it's under the ground. Your open loop wells, and I believe your submerged heat exchanger wells will have a small header to them. But I mean, it's really 90% of it's underground, and sort of out of the way. I'm going to give Jay and Mark a little bit of time. Part of the study was that we reached out to some private energy service companies, or ESCOs, as well as some public utilities, to talk about ownership of a system like this, where once we get into the actual design of this and decide how it's going to be paid for, there's lots of options here, and there's lots of also funding opportunities. There's also some requirements for an ESCO to own a system like this. They're really interested in the size and load diversity, and we reached out to a few of them. But I'll let Jay talk. He knows a little bit more about this. So Jay, the floor is yours.
You bet. So yes, we talked first of all to the investor-owned or public utilities like NYSEG, NYPA, RG&E, and they, while they're not in the business of completely funding these yet, they're very interested because they know that's coming down the pike very soon. New York is in the midst of doing test programs with most of the utilities, and they were glad that we asked about it because they expect that they may be there in time for you. The ESCOs we've talked to, which are energy service companies, basically what they are is the same as a solar company or a power company that would put in something to provide electricity or solar panel arrays. They are very interested in providing the funding for the complete system and then just charging basically what amounts to a regulated surcharge so they get paid back in a certain amount of time. So in other words, if your energy bill, if you're paying $600 a month in the middle of the winter for propane now, and then you go to a full electric geothermal system, and the basic cost of that is just $150 in electricity, they would charge $10, $15, $20 a ton. I'm just throwing numbers out, so don't shoot the messenger if it ends up being higher. So you'd pay a $50 or $60 premium to pay for the energy services that company provides. So if you're paying $600 now, the hope would be that your electric bill that would replace your gas bill would be $200, $150, and by the time you add the surcharge on there, it would be $200. So you're still saving a dramatic amount of money, but you're paying a utility that owns the infrastructure in the ground, just like if it were Con Ed or the water company or something like that, which I know you don't have any of that infrastructure in right now. Which is, just as a sideline, keep in mind when this starts and we're actually at the point of funding this, it may be something that we can help you with on this, where you decide maybe you do want a water utility and maybe you do want a wastewater treatment plant. We can help you go to the state or assist you in whatever inroads you've already made and try to combine those services into one excavation when we're opening up to do the energy network. So the purpose of moving this slow is so that we measure twice and cut once, to use a construction analogy. So we will leave plenty of time to consider all of those things. NYSERDA has stated they don't have any special programs anymore for funding these, but NYSERDA Flex Tech. Now, when I say for funding these, for funding the full, where we start doing the engineering or the next steps that Carter and Justin need to do to get the actual, to decide on the type of system that we are engineering, the civil and excavation drawings, conceptual drawings, and then finally design drawings for construction. NYSERDA can fund that to the tune of 50%. They basically, it's just a matter of course that if we decide to do that, we give them a price that we think it will cost. Maybe it'll be $500,000. That means they'll pay $250,000. And I'm just throwing that out. I don't know how much it will be. And that means that the city of Speedsville, the village of Speedsville, is on the hook for the other $250,000. So that's a big nut to crack, and we know that. So we don't expect you to, we don't want you to panic as a result of that. So there's the combination. Even if you use an ESCO, many of them are very familiar with working. One of them is EcoSave. EcoSave is a company we've worked with on a couple of other projects, and a couple of the local engineering companies we work with in New York that help to shorten the learning curve on actual local laws to get the construction drawings right. They've worked with EcoSave and done high rises in New York City, as well as villages and hamlets outside of New York. And they're funding, they're a highly recommended company. So not only do we have companies we've mentioned before that could do it, we're working with a company that has done it, and we've seen the fruits of their efforts. So there are some great combinations. You will find, if you're not able to, if you don't want to fund it yourself and own it yourself, you will find some ready and able folks that want to do that. So that's one. That's kind of tying in Flex Tech funding and energy service companies. I spent 10 days at MIT earlier this month. We were working with several groups, including MIT itself, which is doing one of these. But we were working with several groups that we had been involved with that did the Framingham, the first energy utility funded thermal energy network in the nation was completed there recently in Framingham, Massachusetts. And it covers several blocks, mixed use like this, just, a lot more population. There were like 270, I think there were 270 residential customers on there between apartment complexes and so forth. They had a school and some other great, it was just a great project. I presented on the installation the last time we met. So that project, as well as what we're trying to do at MIT, has opened up a couple of things. One of the things is that there is an MIT fellow, basically a retired economist named Pat. I'll think of his last name in a minute. I didn't have his notes here, but I have engaged him for extracurricular work. And what he does is he helps us with communities or universities that are trying to figure out how to do this. And he can get this effort purchased in by like the teachers union, the the National Teachers Union, where all their pension money is. So it's a very low risk funding. Because why is it low risk? It's every bit as sure as investing in Con Ed. It's an investment that they will do. This is no longer experimental. This is something that is an energy utility level safe investment. So we can get this added to any number of pension funds. And that gentleman I'm talking about, that's the PhD economist from MIT. If Speedsville chooses to go that route, we would go through the process of getting the value of the utility we're putting in. And by the way, this should be, and I highly recommend that you do everything. You pay for all the heat pumps in all the homes and businesses, everything, soup to nuts. There's ways to do that. So nobody is out any money out of their pocket. Rather, it's worked into this pension fund or bond or whatever you want to call it. That's above my pay grade. That's why we retain great consultants to do that. So we have that option. And then on top of that, I'm going to turn it over to Mark because Mark he won't tell you about himself. We got a hold of him about 18 months ago. He came from a top security clearance at the FBI and the State Department. He worked around the world on large projects like this, power plants and so forth. And he is helping us with our federal grants. And not only that, we're writing some new textbooks for Elsevier and so forth. And he's been tapped to pull those together. So he's involved in a lot of places. And I'd like Mark to share a little bit about what he's in the process, because the timing's good, of applying for something called the Strengthening America Infrastructure Grant. Right, Mark? Is that right? Is
Yeah,
that the name?
yep, that's correct, Jay. So actually, there's two things I want to touch on. One is a federal grant that I'm aware of that I just checked the eligibility of Speedsville, and it does fall within the eligibility zone. And the acronym is REAP, REAP, and it's the Rural Energy for America program, and it's a grant program offered by the U.S. Department of Agriculture. And this, to qualify for this particular grant, it applies to agriculture producers where 50% of their gross income is from agricultural operations or a small business. So a private for-profit entity, a co-op, an electric utility, or a tribal corporation. Okay, but you must be a small business registered with the SBA. Now, what this is it's a grant program for energy improvements, and geothermal does fall within the guidelines of this program. But you would have to get creative as to how you would apply for that, either as an agricultural producer or as a small business. The other caveat is that this particular program, I'm looking right now, closes on March 31st. Of this year. So you don't have too much time to apply for that, but I wanted to make you aware of that. The other one that Jay had mentioned is something that has just come to light that we've been working on just starting last week, and it is something called the Strengthening American Infrastructure Grant Program, and it's actually funded by the National Science Foundation, NSF, and what it is, it's looking to basically strengthen America's infrastructure with new technologies such as the geothermal and thermal energy networks, what's been proposed here tonight. So it's a program that we're looking at, that Jay and I are looking at, and we were brainstorming today, and then this came up this morning, dropped in my lap about some guidance for federal funding. And I had the idea that Jay and I had the ideas discussing it, that perhaps we do need some test sites to develop some thermal energy networks. So what we're going after is we're trying to find 3 participants to work with us who want to employ this geothermal technology, thermal energy networks. And we're also working to develop a mentorship and intern program with STEM students, so science, technology, engineering, and math graduate students. And we're bringing all of this together. So this is all happening right now. So we're also looking at utilizing MIT as well, and we've got one other city. So we were thinking that perhaps Speedsville would be a good candidate to join into the program. Now, this is not funding that's guaranteed to us right now. Again, we're working on an application for a grant that's due at the end of the month. But we think that this,
End of March or April, right?
or it's actually April 17th, but we
Right.
need to have all the paperwork together by the end of the month of
Okay.
March.
Okay.
So, we're thinking that if Speedsville is interested and would be willing to, put up a letter of commitment to participate in this is actually a research initiative. It's actually utilizing AI technology, implementing AI technology and comparing it to standard design software, like what you saw on the screen earlier in Carter's presentation, taking the latest and greatest in technology. So that's what makes it a research funded project. But taking the new technology and comparing how it performs compared to traditional design software. So we're looking for some candidates or some participants who would want to participate in that. And as far as the amount of funding, we're not 100% sure of how much we would qualify. We know that the ceiling for the total grant is $750,000. We're looking to split that between 3 different cities or 3 different organizations, however you want to look at it. But that would be put towards the scoping studies, which was already been done, but maybe towards the test wells, maybe towards the actual design of the thermal energy network, and some of the costs associated with the labor of site visits and so on and so forth. And whatever we can get out of that funding, we would put towards each one of these cities. So.
Well, that's 2 great opportunities that we would want the Speedsville Village Council, Town Council to consider, which could get you some funding to offset any cost, perhaps any costs out of your pocket, which I know what we're trying to do. So I think we're done and we're ready for questions.
Yeah, I think the only other thing we had was I'm going to leave this up. This is hopefully what our roadmap looks like moving into the future. We finished our scoping to determine our technology, and as part of the feasibility, we'd like to do a test well, which will answer all of our unknowns about the subsurface. Feasibility can take 6 months to a year, and then around 2 years for construction for a system of this size. But like Jay said, yeah, that's the end of the presentation. We're happy to answer questions.
Great. Thank you very much. So that's my brain is full. So hang on. I want to ask a question first, and then I'll open it up. But the study that is done to this point, that was a scoping study. Is that correct?
Yes, that's correct.
And then what? And you said that NYSERDA approved that. What does that mean, and what are the implications of NYSERDA approving the scoping study?
It meets a certain level of review that's done by them.
Okay.
So essentially, it's been stamped as approved that it was good enough work, and that we've essentially accomplished all that we set out we would do in the contract with them.
Okay.
And if I may add, Carter,
Go for it.
the reason NYSERDA does this and 100% funded this is what we've done, and part of the reason it takes so long is we've answered all their questions, so they're creating with our help a roadmap for other villages in New York to use to do the same thing, so that they don't have to go through all of the same hoops you did. So that's the main reason they fund this. They don't like to fund things that they already know will work. So for the next ones, they may get funded on a nice sort of flex tech study, but they will. This is publicly available information, and the next folks will be able to look at what Speedsville did and shortcut the effort. So that's the stamp of approval they've given. They've asked all their questions. They've gotten all their answers from us and Speedsville along the way, and now it's an approved scoping study and will be a template moving forward.
Okay, great, thanks. Just wanted that clarified. The other thing I just want to clarify right now is that that Speedsville it's a hamlet, it's a collection of homes, but it's not a taxing district or a political entity of any kind. So it's just like it's sort of like a neighborhood in Caroline. So I think the local government here would be the town of Caroline, which of course is much bigger. But I think that clarification is important.
Yeah. Remind me, is the town of Caroline, is it a collection of hamlets or is there a large town that's called Caroline?
The town of Caroline is 55 square miles. Within the town of Caroline, there are 3 of these clusters of homes that are called hamlets. That's Speedsville, Slaterville Springs, and Brooktondale.
Okay.
But the whole town is not comprised of hamlets. There's a lot of space in between, including state forest and rural ag land and things like that. So,
And remind me, there's a small cluster of homes just to the east of you. That's not it within the town of Caroline, is it?
just to the east of Speedsville is Tioga County.
Okay.
So that's right. It's not Caroline.
Okay.
So I guess I'll open it up for questions. Yeah, if you'd like.
Can you put up the display there, the town where the pumps and all that are gonna be, please?
This one?
Now with the pumps that you're putting in there,
Like the drilling spaces.
pumps. The reliability of them, what do we got on that? How long do they last? Who's maintaining them? Who do we call when one goes bad?
So when you put in something like this, it's similar to a wastewater energy system. If you have a wastewater plant, there needs to be, part of it is, that's where an ESCO may be a good fit for you, because there needs to be a servicing body that does monthly, checking or whatever there will be a maintenance factor built in for how often things need to be maintained. But certainly, yeah, it requires regular service, and that's something that comes out with the specifications on the engineering. So if this isn't owned by Speedsville or Caroline, it would be owned by another entity, which would be an energy services entity that would maintain it just like any power plant or something of that nature. It would just be a smaller power plant, and that's what it is. Similar to if you had a bank of solar panels that had trackers on them following the sun, or even if it didn't, you would need you need a certain amount of maintenance, cleaning of the faces. You would need maintenance of the inverters and so forth. So there is a required maintenance, and that's decided on those pumps and so forth. By the way, a pump has an average life, a circulator of 27 years in a full duty pump, a constant duty pump that's in this genre. So yeah, they will need to be replaced a lot more often than the actual network, because the network will last, several generations, if not more. But the pumps are a mechanical part that will need to be maintained and replaced every, 20 to 30 years.
Got another question. The source, your main line going down to the residences and all that, what's that size?
Do you have any sizing on that yet, Carter? It's not on there, is it? It's okay. Probably on a town this size, I'm thinking about Framingham and their size, probably
Mhm.
around an 8 inch. High
Okay, so
density, probably
your pump then is gonna be what, a horse and a half, 2 horse? Motor?
probably. That's a good guess. That's a good guess. Probably with a variable frequency drive that operates on thermal response.
So an amp draw on this thing per pump is gonna be what?
Don't know exactly. I would have to look at the pump data, but it would be idling much of the time. And in other words, not operating if it's not needed, but a 3 horse pump might draw 3 phase, it might draw 11 amps. So probably somewhere in and I don't know if you have 3 phase there, so that's another thing we have to consider. So it's a little early to say on all that.
What's our backup when the power goes out?
The same backup you have for lights when the power goes out. In other words, if you don't have electricity, I mean, you can put in a backup generator to run the pumps. Say they ask the same things in the big cities when the power goes out. We say, okay, either you have a backup generator or you just don't have air conditioning and heating during that time. That doesn't mean you can't still operate your fireplaces or other backup furnaces if you have a way to do that. Um, but many of the modern combustion furnaces require electricity to run the fan too. So if you have some type of an oil heater or a propane furnace that doesn't require electricity, you can always operate that as a backup.
You have the 4 in this display. Right down through the line that are looking like they go to the residential, then you have 4 other ones. The return one for the loop, then you got 2 other ones right conjunction with each other, and then another one. Those other 3, who's running them? Where's the power source coming from?
That would be part of a common term that we use is common area maintenance. A lot of communities have, for example, city water and they require pumps. Wastewater treatment that requires maintenance and pumps. So that gets figured into the overall utility bill. So once again, if Speedsville or Caroline decides to own that, that would be worked into the common area billing. If it's an energy services company, they would just work that into your $10 or $20 per 12,000 BTU billing, whatever they settle on. I keep saying $10 or $20 per ton because that's what other communities are settling in on. It could be higher, it could be lower here.
There's a question from Zoom. I'll turn it, see if I can see. Milt Tam,
Oh.
can you
Okay.
unmute?
Hi, Mel.
So I got a couple simple questions. I guess I heard you say something about the carbon foot emissions would be 0. Can you explain how that would be?
Carter could probably do the best on that.
I'm sorry?
Carter.
As far as sure, I mean, as far as replacing your current sources for heating, I mean, it takes away all those emissions from the boilers because we'd be putting in a replacement for those essentially. As far as for where your electricity comes from, that would be inaccurate to say. Wherever your electricity comes from probably still has carbon emissions. But as far as the analysis goes for what you're currently using, I think it was 520 tons of carbon a year to heat your homes and commercial buildings there. All of that just becomes heat from the ground.
Do you have any estimate on what the COP of the system will be then?
That's a great question. Jay or Justin, do you have an answer for that?
If Justin may have one, the average COP on energy networks is a minimum of 3. If there's good load diversity, it can go above 7. So
Yeah,
I
I
don't
don't know
think there's good
specifics,
load.
but I was going to say those numbers.
Good.
Okay. Have you calculated it for Speedsville or estimated what would be in particular for Speedsville?
I don't know if they have while Carter looks. I see him furrowing his brow. But I would estimate there is not a lot of load diversity there. You would have periodic times of pretty good, just when I say swing seasons, when you're switching from summer to winter and winter to summer, you indeed may have some buildings that are air conditioning as at the same time as buildings are cooling. I mean, heating, that would be good load diversity. So you'd have snapshots of high COPs. But I would be hesitant to figure anything above the COP of the actual heat pumps plus the energy consumption of the circulators on the system, which is going to be in the neighborhood. Just the heat pumps alone is normally in the neighborhood of 4 COP. So we degrade that to 3 to take in the for a completely a snapshot of a completely all heating system, and that would be a safe number to figure.
And what assumptions do you make about the water temperature being used to heat the buildings?
Carter would know that.
As far as what the ground temperature is?
No, what for the actual buildings, the residences, what's the supply temperature going to be for the?
Oh yeah. I don't know if Carter knows that off the top of his head, but if you're doing forced air, the supply temperature is coming out of the grill is normally about 30. So if you're looking for 75-degree comfort, the temperature across the coil is going to be 30 degrees warmer than that, which means your air coming out of the vent will be north of 100 degrees. As far as if it's hydronic, if you've got an in-floor heating system or radiators that you decide to use, that temperature will come out as warm as 145 degrees.
So I guess so are you assuming that the building, you're gonna use the current radiators or whatever is in the building?
Not likely. And I don't expect you to have absorbed everything I shared. Part of this would be a complete, similar to what they did in Framingham. Not only did they provide the entire energy network, but they also upgraded all of the home's heating and cooling equipment to late model equipment, which fit within what the homeowners kind of wanted. Some of them wanted radiators, so they gave them radiators again. Some of them wanted individual room heat pumps, like that that kind of look like what you would see in a Days Inn with a heat pump under the window. And those are actually very quiet when they're geothermal. You can't even hear them, but you can do room by room heat pumps, which they call package terminal heat pumps, or you can do a central forced air system in which they would have to run, if you don't already have it, ductwork to all the rooms. And so they did any number of variations of those, and many of those they had to upgrade the panels because they didn't even have air conditioning before, and now they have both air conditioning and heating. So there's a panel upgrade that comes in about 50% of the applications. Having walked through Speedsville, I know that several of the homes did have central air conditioning, with usually some of them even heat pumps, air source. So they probably have enough of an electrical panel already, because if you have an air conditioner, it's going to have enough power to do both heating and cooling for your building with a geothermal heat pump. If you haven't been using air conditioning in your home, then you're going to probably need a heat pump panel upgrade for the new heat pump. And that would be something that would come in the next stage. We would figure all that in.
Milton, I think you're muted.
Oh yeah, as Milton's talking, right?
And that may have been my fault. I was clicking around.
Thank you. I
Yeah,
was
sorry about that.
So I'll call on Tim Murray, who's in Zoom land, and then we have a question here at the Speedsville Community Center. So go ahead, Tim.
Yeah, thank you for this presentation. I'm trying to get a, a clear sense of the funding structures for subsequent phases. Because you had mentioned that, if I understood you correctly, that the next phase there were grant opportunities that would be a 50% match. My question is, if one were to go to an ESCO model, at what point would the ESCO then assume costs for these phases?
That's a great question, Tim. For an ESCO to assume it, the first thing they're going to do is they're going to have a meeting like this with the town council and get a quorum. In other words, enough of a majority vote, which we kind of have. Everybody's cooperated, but we would need all those people to say, yes, we're going to sign a contract that says we will enter into this phase where the ESCO will pay for everything from here on out. Now, what the ESCO will do is they will indeed go through complete engineering. They will use NYSERDA dollars to help fund the full engineering documents, and then they will install the system. They won't go that far without knowing that it will work. And that's what we've provided, something that says it's workable, or they may determine it's not workable. They may say, this is not enough money. It's not worth our time. And so that's a very real possibility because of the size of Speedsville. Even though, I mean, you heard Carter say you have the chance of saving $250,000 a year cumulatively. I don't know what that turns into profits for an ESCO. So I'm going to jump to the next stage. The next stage would then be possibly selling the system, and that's where we had involved this economist who might be able to sell the whole system as a bond or an investment to a pension fund. So we have that vehicle too. The ESCO, we haven't tried to get an ESCO involved, or at least we haven't really gone down the road of getting ESCO involved in something this a community of this size, but we consider it one of the most important missions we have right now, because this is where energy poverty and the greatest need often is in small rural communities that are experiencing very high costs for heating in the winter. So part of it is we're trying to find a model that will work not only throughout New York, but nationally. So we have a few steps there, but the ESCO model, you wouldn't pay another penny out of your pocket if they signed on.
Thank you.
Yeah. Thank you, Jay. Is there questions?
I see Michael Brown's hand is up.
There's sorry.
Mark, my
Yeah, okay.
after.
Yeah, I see that. Thank you. Go ahead, Mike.
I was so this was a scoping study, is that right? And then
Yes.
on the timeline, I saw another scoping study listed. Maybe that was this one, but then a feasibility study as well. And I'm just wondering if you can, yeah, so I see scoping. Is that the current one that just got completed, or is that
Yeah,
another?
that's the one that we just finished.
Can you clarify the difference then between a scoping and the feasibility study?
Yeah, scoping is sort of a less committal analysis that either approves the possibility of a geothermal system on site, or essentially denies it. There are some places, unfortunately, we get hired, and the ground or the aquifer, for whatever reason, doesn't quite work out, or it's not going to be economic. This scoping study gave us the green light on all three technologies that we considered here. We, after our life cycle analysis and after some geologic and hydrologic study, They can all be economic. They can all work in this area. And so now that we've gotten the green light from the scoping study that it's viable, then we move on to the feasibility, which usually decides on just one technology, sometimes more than one. But that feasibility is a study with the intent to design, which will then move into construction. Does that make sense?
It does.
Okay.
And then I just had a question on the sizing of the overall system. What would happen if more houses got put up in Speedsville? Um, does the system allow you to either, drill some more holes to make it larger? And also, if these are, I imagine, relatively old homes, um, weatherizing them and making sure that they're heat pump ready, has that been considered? And would you want to put a heat pump in a home that, couldn't, I know you want to get them to certain levels of weatherization for the heat pump to operate efficiently.
I'll answer that. As part of the next phase, we definitely there's a holistic approach. When we go into the full design, there the tightness and heat pump readiness of the home is considered, and there is a tremendous other bucket of money for doing those energy surveys on the home. So we'd pull in another consultant that gets funded by NYSERDA, I think 100%, to do a weather analysis, and then there would be those costs, and we would help you decide whether to put, and those costs, a lot of those costs are covered by NYSERDA and the state too. So we would help facilitate that and decide. We get really outside the lines. The only requirement we have to be involved in those things, we wouldn't do the weatherization design and studies. We would have another consultant in to do that, but we'd make sure it's done right, because we have been on, as you know, from asking the question, we've seen too many homes where they put a perfectly good heat pump in there, but it leaks like a sieve, and the heat pump never turns off. And so they just use an incredible amount of energy, even from a heat pump. So the weatherization comes in the next phase as we validate what size heat pump would be going in, how much it would cost, and what type of system, and whether the building is heat pump ready.
Thank you.
You're welcome.
Residential and commercial.
Could you hear that, Jay? I
didn't quite. Go ahead again.
Is there a price difference in commercial and residential use?
Oh, yeah, from the overall system, usually there is, because commercial has a greater demand and longer run hours. So it's not drastic though. And a lot of times it's more advantageous overall because there's more energy used. But every system's different. We're still in a very front end part of the industry, but there is a little bit of difference. Not a lot I've seen so far.
Deal though, I got one more quick. To get the pipeline laid in the ground, if you're crossing somebody's land, they're absolutely against this. What are you gonna do?
Yeah, that's something we have to address in the early stages. And understanding, if I'm not mistaken, there are no utilities in the ground to speak of. So we would have to address that. Maybe that we'd have to have a buy-in from the everybody that's involved. And then that pipeline area would become a right-of-way as part of this. And that's one of the things we have to go through on the feasibility study, is get the pipelines laid out, see if there's any objections. Then it really does become a right-of-way, where, as you well know, if you have homes where there are utilities, you don't really have a choice if somebody comes and digs up your yard to fix a utility because it's in your yard. So that all those contracts and understandings and town meetings have to take place, which is why it takes 6 months to a year on that part.
Not follow up.
Who's in charge of the yay or nay on this, the final?
That might be a question on for Mark. I mean, we're completely yay on moving forward and at least getting you on an application grant for the Strengthening America grant and maybe even the other one Mark talked about. And we are willing to get an ESCO in and talk to you about this now that we're this far along. So we're open to all of the options right now. So it's a matter of, is Caroline and this hamlet of Speedsville open to having another meeting now that we have this, and then we'll have Carter and the team and get Mark involved and get this get another meeting set up.
Still get charged.
So from my understanding, the getting the right of ways would be with individual property owners. That's not a
So
town.
then it would just go under the, what the hell's the word? And then
That's,
domain if it goes that far.
I think that's not what Jay was saying. This would be,
No, but I'm saying if somebody's strictly against absolutely none,
yeah,
but the next guy right down wants it, and you gotta go across, then that's what they're gonna go to.
possibly, but the first option I would think would be to design around that.
Yeah, I would think that you put in the street, right? Just follow.
Yeah.
Yeah.
Streets, and then the tax would go into the private locations with approval.
Right.
Just like you would
That's-
after something
Yeah.
like that.
Yeah, we would go in the street with the with the main. And so if somebody didn't want a tap coming into their place, that would be I know there's going to be exceptions possibly, but when I think about the way it's laid out, I think the main line and the pumps are all going to be in what I would consider public right of way, like the park, the square around the park, and the street, other public streets.
Aaron, did you?
Yeah, so with this system, I'm just trying to understand a little bit. We are delivering what temperature water to the houses? So are we
Okay,
geothermal system, or you're giving me 50-degree water and then I use a heat pump within my home to increase it? Or this is not like a warm earth program where we're delivering 120-degree water?
that's exactly right. And I'm so glad that you asked that, because that is the number one misconception. Another term we use for these systems are ambient temperature loops. They basically come in at the temperature of the earth. And that's the beauty of it, because there's really no insulation needed for the piping in the ground. So you get those pair of pipes into your home. One's a supply pipe for your heat pump, and one's a return pipe for your heat pump. So your heat pump takes that 55-degree fluid. I'm just using the average. And if you're in the
53 in
heating,
Speedsville.
what is it?
53.
53. It takes that 53-degree supply temperature, and if it's the winter time, it pulls heat out of it and sends it back into the loop at 43. And if it's summertime, it takes the 53-degree temperature and sends it back at 63. And then by the time the loop can operate, this is the beautiful thing. These heat pumps are what are called extended range geothermal heat pumps. So they operate very happy at any temperature between 25 degrees, which I know is freezing, but we use a heat transfer fluid, and 110 degrees. They're completely within specs at those temperatures, kind of the same as your low ambient air source heat pumps. It's just that you will never hit those temperatures. So we try to maintain that between about 40 and 90 degrees year round. And that gives that big loop a chance to share energy between your spaces. And people always wonder, oh, what if I'm down the road from the next house from Bill, who's taking all the heat out of the circuit? We can show you in the models, it doesn't make a dollar difference in a year. These heat pumps, as long as they get above 25, 30 degree Fahrenheit, they're going to operate at very close to the same efficiency as if they're getting 55 degrees. Because there's plenty of BTUs in the water. It's just a matter of extracting it efficiently, which is what these heat pumps are designed to do. So we do have, so that's the first question we get is, I don't want to be down the cascade. It all works out. It all averages out anyway. And we can maintain that loop temperature at always between we can maintain it as tight as 40 to 70 degrees year round. But we want to kind of give it a little bit wider because the electricity deficit we get from running the pumps too hard doesn't pay off in the overall system performance. The wider we can keep that temperature band, the more efficient everybody operates. So yeah, it is an ambient temperature loop. Your heat pumps are designed to extract and reject energy to that, and that's all there is to it.
Jay, how about I share my screen and I can do the put my slide up that shows the diversity and cascade.
I love that idea. Mark's really good at teaching this. He's writing the textbook on it for Elsevier, or he's assembling the image, the data. Go ahead, Mark.
Okay. All right, give me 1 second here. Let me pull this up. All right. So this is from a presentation I presented to the UA last week or week before, explaining thermal energy networks to the pipe fitters unions. Let me go back.
We need to give permission for him. I don't know how that works.
Can you share, Mark? Do you have a button?
I just requested, so somebody has to approve the request.
That'll be Mark. He'll do it. Your co-host now.
All right, thermal energy networks, share. All right, we all see the PowerPoint?
Yes.
Okay. So what we have here is a one pipe system, okay? ATL is not Atlanta, it stands for ambient temperature loop, okay? So we have our geothermal loop over here. This is an example of a closed loop. And we're targeting a 75-degree inlet temperature. Now, keep in mind, this is all just theoretical for demonstration purposes, all right? So we go into a heat exchanger here at 75 degrees, whether it's heating or cooling season, will determine basically what this discharge temperature is going to be. So for the purpose of this demonstration, let's just assume that it's going to be that we're in the summer mode. Okay, summer mode is represented by the numbers in blue. Okay, that's telling us summer mode. Okay, now also we see that we have 3 different types of stakeholders on this loop here. We've got a data center. A data center is a cooling dominant, meaning that it's always putting heat onto the loop, which is for this example is the equivalent of 10 tons. Then we have an apartment building, which has mixed use, which has a generally even use of heating and cooling BTUs, okay? And then we have a heat dominant consumer or stakeholder on the loop, which is, let's say, an industrial plant that does that needs high temperature processed water, which is consuming 400,000 BTUs, okay? So all on the same loop, you've got somebody who's cooling dominant, somebody who's trying to heat all the time, being heating dominant, and then somebody that switches back and forth all the time, all right? So what ends up happening is you have one primary circulating loop, circulating pump here. The heat, the ambient temperature loop grabs heat from the earth, okay, and circulates. Now, one thing you'll see is that this pipe size is 3 inch all the way around. It doesn't matter how many people you put on this, it's 3 inches. And I'm going to demonstrate that here in this next slide, okay? So the other great thing about this is that this is completely self-balancing. So if you add more people to it, this isn't like a traditional two-pipe system where if you add people to it, then you have to worry about, well, is there enough capacity on the loop? Because you end up sizing when you put this in for a maximum amount, okay? So let's say you anticipate down the line, you're going to have 10 million BTUs of usage, but you only have 100,000 BTUs to connect to it now. Well, that's fine. You just size it for that. And then this loop is pump controlled. It's not control valve controlled, which we're all used to, or I should say those of us in the trade, if remember the audience. So what ends up happening here is this is in summer mode, okay? So we have a heating dominant. We have this person here, this stakeholder producing 300,000 BTUs, and we have this other person here producing 240,000 BTUs, which is about 10 tons, okay? So that means that we should, in theory, in a traditional system, have to reject 540,000 BTUs to the earth, okay? Because 240 and 300,000. Now you have to remember this guy here is not cooling, so it's not rejecting heat, but it is absorbing heat. And if we look back up at our heat exchanger, though, instead of 540,000 BTUs, we're only rejecting 140,000. Why? Because this guy consumes the 400,000 BTUs. So 540,000 minus the 400,000, you're only rejecting to the earth 140,000 because this guy is you're basically sharing the BTUs. So whatever the energy is that these guys create that would normally be dissipated to the environment is actually being recovered and used by this stakeholder here at a reduced rate. So basically everybody would have a BTU meter, an energy meter, at each stakeholder's inlet to their home or the outlet. It's actually the outlet because you would address the temperature drop. And so your costs are reduced for BTUs because you've already pulled the heat out of the ground. Now you're just circulating it across through the loop. Okay. And so one of the primary concerns that we have with this type of design in a one pipe system is something called cascade effect, which is the progressive temperature change as somebody adds heat or takes heat out of the loop. But as you can see here by these annotations here, in the summertime, it's coming out, it's designed for 65, right? Well, then it goes into this guy who's heating dominant, all right? You're getting thermal mixing, okay, in this loop as the water moves through the loop. So it's actually going in at about 56. It's coming out at 36, all right? But then as it gets to the next guy, look, the temperature starts to rise, okay? And as it continues down the line, it continues to rise even more until, look, it's going into the data center at 65. Well, 65 is where we started out at. And this system is designed to go in at 75 degrees, all right? So there's another thing called diversity, all right? And the diversity is the variation in the stakeholders here, all right? So variation being this guy here is cooling dominant. This person is heating dominant. And when we look at their consumption, there's your variation. So that's the diversity. And so counterintuitive, actually, the more people you have on the loop, the more stakeholders, the more diversity, the more even distribution you get of the thermal energy. All right. And these thermal energy loops are very easily scalable. There's no limit to the amount of stakeholders you can put on the loop. There is a total limit, though, of the amount of BTUs that the loop can handle. So that's why I said, when you size it, you size this for future expansion. So if you expect in the future to ultimately have 20, 30 homes on this, and as I said, 10 million BTUs, then you size it for that, okay? And if you only connect one person in the beginning, it's fine because this pump here is VFD controlled and will ramp up and down. Same with the pump that circulates water down to your geothermal loop, okay? They're variable frequency drives, meaning they vary their flow rate based on demand. And that demand is, it's looking at always maintaining this 10, 15, 20 degree delta T here that we have across the heat exchanger, okay? So it's not controlled by differential pressure, which is a traditional system, which looks at the differential pressure between the supply and return line, which then tells the control logic whether to speed up or slow down the pump, okay? Because in theory, if all your control valves open, then your DP goes to 0 and it tells the pump to speed up. So now, managing temperature cascade, all right, same diagram, all right? What I've done in this one, though, is I've added a cooling dominant stakeholder onto the loop after the fact, okay? Cold storage. So this could be a grocery store. Grocery stores are cooling dominant, all right? Now, if we look at the loop, what did that do to our loop? So we still have the same discharge temperatures, right? 85 and 65. We're still maintaining the 75 degree on the loop. We still got the 75 coming back in, but let's look at what the differences are. So in our previous slide, remember our ambient temperature loop was 75 and 36. Well, now look what happens to our loop over here. We're at 78 and 54 because we added this cooling dominance. So this guy's dumping a bunch of heat on the loop. Now look at the inlet temperature. It's 69 degrees, okay? Whereas on the other slide, with less diversity, it's 56 degrees. So again, this proves that diversity, the more diversity, the better the system performs, all right? And as you go along, you can see progressively that the temperatures are increasing. Now, one thing that I want you to notice here is that we added essentially 10 tons of cooling to this, all right? Yeah, this is 20 tons. This is 10 tons right here of cooling. All right. We added 10 tons of cooling, but look at our pipe size. It's still 3-inch. All right. There's no change. All right. Now, what did change is this pump, the GPM that this pump is moving now. See, 52 GPM in summer. If we go back here, what was it moving with just 28 GPM. So the system responded because it's pump controlled. All right. So the pump sped up to accommodate this new stakeholder on the loop. And if we look at our BTUs that are being discharged now, it's 260, right? In the last slide, what were we? We were 140. So we went up by 120,000 BTUs, which is this stakeholder. Well, it's being rejected by the heat exchanger because there's no other heating dominant in this particular scenario at this snapshot in time. There's nobody else to absorb that heat. Because remember, this guy here is absorbing the 400,000 BTUs from this guy here. So we're left with nothing but to discharge that heat through that heat exchanger. Now, in theory, the apartment building and the data center ultimately are also producing domestic hot water. So in theory, the apartment building and the data center would be consuming some of those BTUs, okay? But it's just not shown in this simplified representation of a thermal energy loop. So good cascade, good temperature cascade equals a good temperature change in a sequential manner, which we've shown here in this thermal energy network. Now, what causes poor temperature cascade? So improper flow rate. And as we've shown in this example between these two, right, the pump sped up from 28 GPM to 52. Improper sizing of the pipe. Well, the system, the design software automatically takes care of that. I've just shown that we can add, okay, another stakeholder to this unit, to this system here, okay, and we won't have to change the pipe size. So as you add residences or other stakeholders onto your thermal energy network, you're not having to go back and dig the street up. All right. Improper insulation. Okay. Well, this is an ambient temperature loop, so your pipes below grade won't necessarily need insulation, but things like your equipment, your ductwork, maybe you do have some lower temperature pipes. Okay, like perhaps in the last slide where it was 36 degrees, where you might need insulation. Again, it's dependent upon the application. And then insufficient diversity. All right. So this here perfectly represents what happens when you have more diversity. So we had 3 stakeholders here. We added a 4th. We added 10 tons of cooling, and the system starts to perform better. So that's all I wanted to share about the actual performance of these. So is there any questions about these slides?
I love that. That's why I don't have to travel as much, because you can present this now to pipe fitters. I'm sure Aaron loved that too, but I don't know if you talked over anybody else's heads, but you did a great job for my part.
Great. Thank you. Thank you very much. So I guess Oh, Mike,
We've got a lot of the positives. What about the negatives, such as in the food? Is there any propylene glycol or corrosion resistant materials that will contaminate the well water that we all have around here?
No, so let me go back. I got this.
Yeah, thank you.
We put the slide back up. Share. Okay, so there's something called hydraulic separation, all right? And that's what this heat exchanger is, okay? So this is called a plate and frame heat exchanger here, all right? And the water that's in this ambient temperature loop never ever mixes with the well water. Okay, it never actually physically comes in contact because there's a metal plate there for which the heat transfers through from one side to the other, depending on whether you're in heating or cooling season. Okay, remember the laws of thermodynamics. The second law, heat travels from hot to cold. Okay, so there's never any, it's hydraulically separated by the heat exchanger. And then within each one of these buildings, let me see if I have a slide here for it. No, I don't. I don't have it. But within each one of these buildings themselves, okay, it's either the heat pump, which has its own heat exchanger, which hydraulically separates the heat pump from the ambient temperature loop, okay? Or you have, in a larger building, you have another one of these types of heat exchangers, okay? And then each one of these loops, these in the building has its own loop. Oh, here we go. This is what I was looking for. So this is what it looks like inside of let's say a commercial building. So you grab water off the ambient temperature loop, it goes into the building through a heat exchanger, and then you've got another one of these, loops. The secondary loop is called a decoupled secondary loop, which means whatever happens on this secondary loop doesn't affect the primary loop. It's decoupled. It's completely independent. It flows, okay? And you have these circulator pumps here. These circulator pumps replace the balancing valves. This is where the self-balancing feature comes in, is these pumps are sized for the demand on the building itself, okay? So to answer your question about the glycol, there could possibly be propylene glycol in this ambient temperature loop. Propylene glycol, though, is food grade safe, okay? And now they actually make one that's 100% biodegradable that can have incidental food contact. It's made by Corchem. And so this glycol can contact food and you can consume the food and be safe. But the use of glycol is dependent upon the conditions and the design of the system if you're going to be reaching near freezing temperatures in this ambient temperature loop. So in this particular design where we're reaching 36 degrees, it may be conceivable that the loop may require glycol to prevent freezing. Okay, now without glycol, then this becomes a typical closed loop system where you have to add in your inhibitors, just like any other closed loop hydronic system in a building.
Great. Thank you, Mark.
So what's the probability of earthquakes happening because of the drilling?
I didn't hear the question.
What's the possibility of earthquakes happening because of the drilling?
It's not deep enough for that. The earthquakes you hear about that are popularly espoused with geothermal have to do with very deep drilling, multiple kilometers, and then fracturing the rock down in the ground so they can get communication. Those are called enhanced geothermal systems. That is not in this genre. This is just the classification of water wells, basically.
Thank you.
Great. Thank you. Another question at the community center?
So you're taking the water out and just putting it back into that well. How's that gonna work out now? Up to 1,000 feet too, right?
Yeah.
Yeah.
So you're pumping water out and we're using that, right? And a closed loop comes out of the well or out of the wells, or is it gonna be pumped out and then go away into another one?
Yeah, the water is
The
pumped out
loop.
of.
Go ahead.
If it's closed loop, it's just conductive transfer, and that's what Mark has indicated here. One of the methods Carter identified is open loop, but it's non-consumptive. So essentially, it's a closed loop with an aquifer. It's like if you imagine a fish tank pulling water out of one side of the fish tank, running it through an exchanger and dropping it on the other side. What Carter said when he's talked about the 1,000-foot separation is we have it far enough separated that there is not thermal communication between the supply well and the injection well. So it's non-consumptive, which is considered a very environmentally friendly, EPA regulated friendly system. And by the way, New York considers it friendly, which is a very hard state to appease. So they approve those systems too.
The other thing too is you said that you're gonna have glycol in the system and it's not gonna leak or it's not gonna contaminate ever. Anything that's man-made will break.
No, I didn't say that we were going to have glycol. I said that it depends on the design of the system. Does the design of the system warrant glycol? And yes, anything that is man-made, any mechanical device that is man-made will eventually fail. Does it fail in a year or does it fail in 100 years? HDPE piping, according to the Piping Plastics Institute, has a rough life of 100 years.
But these pipes, they're plastic, you said PVC, plastic?
No, high-density polyethylene. They're very flexible. And you got to remember too, the glycol itself is 100% biodegradable. It's rated for food incidental contact, so it's 100% safe for the environment.
Right now.
And then on top of, I'm sorry, what was that?
Said right now they're saying that, but I guarantee a large quantity of it's gonna do something.
Yeah, so I. So
I don't know
anyway,
what to say. I mean, that's just it's rated. It's published data that it's food grade safe. So by the USDA. So I have no argument with that.
great, thank you for addressing the concerns. So I guess for the next steps, we need to consider how we're going to approach the next study. Is that correct?
Yes.
Okay.
Yes, we can do a little bit by follow-up email, but we will follow up with an email and say, okay, would you like to do the ESCO, consider the ESCO approach, the NYSERDA FlexTech approach, and Mark will send over a letter of support request for getting involved with the grant. So all we're doing here is trying to take the financial burden as much as possible if the town decides they want to move forward, or the hamlet.
Great.
So we'll send a follow-up that's pretty clear and concise. And
Okay.
I know you have a recording. We'll send notes from also transcription notes from the meeting today with really nice summary and bullet points.
Okay. Wonderful. That'd be perfect.
All right. You bet.
That sounds great, Jay. And so thanks to you and Carter and Mark and Justin. I really appreciate it. Yeah.
You bet. You bet. And we're always here. You can ask any questions. We'll have more meetings as needed, okay?
Okay. That sounds good. That sounds good. Great. Well, thanks for joining us tonight. Very
You bet.
helpful.
Good.
Thanks for having us. We'll be in touch. Thanks, y'all.
Take care.
Okay.
Bye.
Yep. Take care. Good night.
So who is on the committee for this?